Okay, so we're going to go ahead and do a quick lesson about simplifying square roots and radicals. So our objectives here are to review the properties of square roots and to simplify radical expressions. First things first, we want to know what this radical symbol looks like, and you've seen it before. It's taking the square root of a number. So when we say the square root of 16, what we really mean by that is the positive square root of 16. So you know that the square root of 16 equals 4. If you were to see a negative in front, it means the negative square root of 16. So that would be negative 4. So you need a negative in front to specify whether or not we're talking about the positive square root or the negative square root. When we solve equations with square roots, we're going to, if we had something like this, x squared equals the square root, or I'm sorry, if x squared equals 16, the way we solve that is square rooting both sides. When we square root both sides, we need to talk about two solutions here, both the positive and the negative. But that's only when you square root both sides of an equation. Okay. Properties. So there's a multiplication property of square roots that says this. For any numbers where a is greater than or equal to 0 and b is greater than or equal to 0, then the square root of a times b can be broken up into the square root of a times the square root of b. So, for example, the square root of 12 can be broken up into the square root of 4 times the square root of 3, since 4 and 3 are both factors of 12. The division property for square roots, if you had a division problem like the square root of 3/5, that can be broken up into the square root of 3 over the square root of 5. And we'll talk about how to deal with something like that, how to simplify a radical expression like that. All right, so here's what we're going to do. We're going to simplify some radicals. So when simplifying radicals, I like to have a list of perfect squares. So like starting with 4, that's 2 times 2, 3 times 3, 4 times 4, so on and so forth. 36, 49, 64, 81, 100, and the list keeps going on. The reason I want that list there is because it helps me to simplify these radicals. When I simplify something like the square root of 48, what I do is I make a factor tree. On the left side, I pull out a factor of 48 that's in my list of perfect squares. So I need to think about that. What factor of 48 is in my list of perfect squares? And the answer is 16. So this would be the square root of 16 times the square root of 3. The reason I pull the perfect square off to the left is because it reminds me I need to keep going. The square root of 16 is 4. Whenever I'm done with one branch on my tree, I like to circle the end. So square root of 3, there are no perfect squares in my list, so I cannot keep going. So that's root 3 there. So my final answer is just going to be the product of these two, which is 4 root 3 is how we say that, and that's how we write it. All right, so square root of 72, same thing. Now, I want to show you what happens if I don't pull out the biggest perfect square. So the biggest perfect square that goes into 72 is 36, because root 36 times root 2 is the square root of 72. But let's just say you pulled out a 9, because root 9 times root 8 is 72. Now, this works because 9 is a perfect square. The square root of 9 is 3. Except I can keep going over here. Square root of 8, I can factor out a 4. So this is root 4 and root 2. The square root of 4 is 2, so I'm done there, and I cannot simplify the square root of 2 anymore. So what do I do with all these numbers? Again, we're multiplying. So 3 times 2 times root 2 is 6 root 2, which, by the way, I would have gotten that if I would have done root 36 times root 2, which is just 6 root 2. So this is quicker. So you always want to see what the biggest perfect square is. That's a factor of your number under the radical. All right, denominators containing radical expressions. Remember our rule. Our rule says we can break this up into the negative square root of 5 over root 7. You cannot have a radical in the denominator. So I'm going to show you how we get rid of that. The way you get rid of that is to take whatever's in the denominator and you're going to multiply by the magic number 1 here. I call it the magic number 1 because we're going to multiply by root 7 over root 7. This whole thing is equivalent to 1. And when you multiply something times 1, it doesn't change the value. So with fractions, multiply straight across. So we get negative square root 35 over root 7 times root 7 is root 49. What is the square root of 49? 7. All right, next we want to ask ourselves, are there any perfect squares that are factors of 35? Can we simplify the numerator? Square root of 35. Let's go back up to our list. 4 doesn't go in, 9 doesn't go in, 16, 25, nope. So there are no perfect squares. So that is completely simplified. Let's try one more example. Root 2 over 3. We're going to break it up. Root 2 over root 3. In this case, the denominator is root 3, so my magic number 1 is going to be root 3 over root 3, which would give me on top root 6 over, now I'm going to show you a little trick here. We know that root 3 times root 3 is square root of 9, but we also know that the square root of 3 times itself is just 3. In other words, the radical and squaring it, these are inverses, so we just get what's underneath the radical. So root 6 over 3, and that's fully simplified. All right, in these notes, you have 15 practice problems to do here. So I would like you to go ahead and do this on a separate sheet of paper. So if you need to pause the video to write down these problems, that's fine. But then you can turn these in to me for a homework grade. And that's it for simplifying radicals.